Okay, for this problem, we want to find out if it needs a free body diagram. What they're asking us for is velocities and accelerations, so it's not a dead giveaway. So what you do is count the degree of freedom. In this case, the drum can rotate, so that gives 1 degree of freedom. If you stop the rotation, you have to ask yourself, can anything still move? And the answer is no. Now, if you think that this thing sways side to side, you need to be able to write the free body diagram of this, and what you'll find is that there are no horizontal forces on the object. If there are no horizontal forces, then the object can only accelerate or change its velocity vertically. So if it starts off with 0 horizontal velocity, it'll have to remain with the 0 horizontal velocity. So really there's only 1 degree of freedom. So because there's only 1 degree of freedom, if you are given one velocity term, which you're given an omega, that means you can find any velocity that you want. And that's what they ask for, is the velocity of a point. And you won't need a free body diagram for that. Because they also give you one acceleration term, you can find any acceleration. So if you notice, that's what they ask you for in the second part, or the third and fourth parts of the thing, is to find the acceleration. So that means that you do not need a free body diagram. Okay, so when you're relating the motions together, you can either use ropes and pulleys, special points, or vector loops. In this particular case, I don't see any real good place to draw a vector loop on this. That often happens when you have rotating bodies like this, like drums and gears and things of that sort. So I'm going to use special points for this. Okay, to do special points, you want to locate the number of rotating bodies. There's only one rotating body, it's that drum. So now you look for the special points. There's a special point here at B because you want to know something about it. That's the only reason that B is special. On previous exams, I would draw pictures of these things, and I would stick some arbitrary point over here, just some point Q or something. And never ask for Q or anything else. And Q is not special unless you want to know something about it. So don't be fooled. Anyway, so B is special because you want to know something about it. The center C is special because you know that if it's doing anything, it's moving in a vertical line. And P is special because it's touching the rope. Okay, so there's 3 special points. Because there are 3 special points on one body, there's 3 minus 1, 2 special point equations. So at most, I'm going to be able to write 2 special point equations. Okay, since they want velocity, let's start with the velocity. You should always start with velocity anyway because the acceleration terms have omegas in them, and unless you know the omega, you'll need to calculate it. Often on exams, I will give you the angular velocity and ask you for an acceleration, and that's an indication that you should just jump into the acceleration terms. Anyway, so I'm choosing A and P. The reason I choose A is because I know something about it. I know it's going vertically. And the reason I choose P is because I know it is in temporary contact with no slip with that rope. So I know something about it. So that's why I choose A and P to begin with. The reason I put A on the left and P on the right is because I've got the table of contacts memorized, and I know that the velocity of P is going to end up being 0. And I always like to put my zeros on the right-hand side. It just, to me, it makes my equation look a little neater. But you don't have to worry about which one. You just pick one, right? It doesn't really matter. But anyway, that's why I did what I did. So I write velocity of A equals velocity of P plus omega cross R, and this R goes from P to A. So if you're going from P, yeah, this should have been C, the center of the point. All right, my mistake. This should be the velocity of C. So everywhere you see a point A, it should be a point C. Okay, anyway, my mistake. I wasn't looking at the picture. The reason A is not special is because they're not asking me for anything about A. So if you notice, nobody asked me anything about A. So I'm really using P, C, and B. Okay, so anyway, velocity of C equals the velocity of P plus omega cross R. R goes from P to C, so that is 0.1, and it's to the left. That's why it's negative I. And omega is going to be in the positive direction, counterclockwise, which is the positive direction, which is 4. Okay, there are no V-wells because C and P do not get any further apart or closer together when it moves. And so that's why that's 0. And then I'll go ahead and write the velocity of B equation, B to P. Oops. B to P. And the reason I'm using B and P and not B and C is because I know more about P than I do about C. And it's just going to make the algebra a little bit easier. That's why I choose B and P. But you could use B and C, no big deal. So anyway, the R goes from P to B. So P to B is going to be the diameter, 0.2, in the I direction. Okay. The next thing I do is I'm going to plug things in. So in the blue, velocity of A, I'm just going to bring in this equation down here. Velocity of A is, now P is equal to 0 because it's in temporary contact, no slip, with the rope. The table says that, under those conditions, the 2 points have the same velocity. The rope is fixed, so the rope has 0 velocity, and that's why P has 0 velocity. And then I plug in, or I do the cross product. K cross I is a positive J, so the cross product gives me this term right here. And then I just simplify a little bit and just grind it out with some algebra. So I get velocity of C, not A, velocity of C is equal to negative 0.4 J. The 0.4 is the magnitude of it, and the negative J is the direction. So on a test, I would write that's equal to 0.4, and it's down. Okay, so then you bring the second equation down, and you substitute in for that one. Velocity of B equals velocity of P, again, temporary contact, no slip, so P is equal to 0. You do the cross product, you end up with this negative 0.2 omega J. And then just simplify a little bit, boom, you end up with that guy being a negative 0.8 J. The 0.8 is the speed, and the negative J is the direction. Negative J is down. Okay, so now you want to find the accelerations. So the easiest thing to do is just to mimic what you did with the velocity. So I wrote between A and P, so I'm going to write one between A and P, just like I did before. This time it's alpha cross R. You notice it's the same R that it was before. That's why if you mimic it, you can save yourself a little work and a little time. And then you have this this term, because of the two-dimensional thing, minus omega squared R. And then again, there's no rel terms. There's a bunch of them normally, but there's none. They're all 0 because C and P do not get any closer together. So those are all the rel terms are 0. And then the next equation, acceleration of B equals acceleration of P plus alpha cross R minus the omega squared R. And so now we do just like we did before. I'm going to do the cross products. So I'm going to put in here. So I'm just bringing this guy down. I'm going to do the cross products and plug in what I know. The acceleration of P. Okay, the table says that P is, well, we know that P is in temporary contact, no slip, with the string. What the table says is that in the plane direction, which is this direction here, up and down, in that direction, the accelerations are the same. But in the normal direction, which is horizontal, we have no idea what they are. They're probably different. And so that's what I write here. I say, well, AP could have a term in the x component, horizontal, and I'm assuming it's going to the right. Who knows? So if I solve for APX, I get a positive. I'm right. It's accelerated to the right. If I get a negative, I'm wrong. It goes back to the left. So that's why that one is different than up here. So if you notice, up here is 0 because the table says that they're equal. Velocities are equal in all directions. Here it's only equal in the plane direction, which is up and down in this case. Okay, and then I do the cross products, no big deal. I do it like I did before. And then you've got your omega term, which is just bring it down. Nothing really fancy about that. And then I just simplified a little bit. Plugged in the numbers for alpha and omega. Okay, and then you bring down the second equation here. Acceleration b equals acceleration of p. Same thing as before, right? It's only 0 vertically. You don't know what it's doing horizontally. Whatever you plug into this guy, whatever you plugged in here, you have to plug into this one as well. So just be careful what you do. Okay, and so then you just finish the rest of the things, do the cross product, etc. And that's what you get over here. So it just simplified it by plugging in the alpha and the omega. Okay, then I'm going to bring down this Boole equation. So I bring down a y. I know that this guy is going vertically. If anything, it has no acceleration horizontally. If you think about the forces on this, it cannot accelerate horizontally. And then the right-hand side over here comes down here. So that's the right-hand side. And then you just clean it up a little bit. So here I pull off the j components. And so again, that should be the center. ACY is equal to this term right here. It's a negative 0.75. And negative means that the AAY, I assumed it was up, right? Because I said the positive AAY is in the positive j. I get a negative number that says, oh, you were wrong about that. The thing accelerates downward. Well, obviously it does, right? I mean, if you drop this thing, it's going to unwind and go down. So that's what the negative means. It means that when I put in plus AAYJ, I was wrong. It should have been in the opposite of j. So anyway, it's a negative 0.75. On the test, you would write that the acceleration is 0.75 and the direction is down. Okay, and then now you take the i's of that equation. Over here on the left there are no i's, so it's equal to 0. And then you pull off the I terms here. So you have APX and you have a 1.6 right there. So you solve for APX, you get a negative 0.16 or 1.6. What that tells you is that what you thought that APX went to the right, you're wrong, it goes the other way. And so I can say that the AP of the X is equal to 1.6, and it's left. That's from that negative sign. Okay, so now I'm going to bring down this next equation, AB equals this stuff here. Brings it down here, and then I just massage it around a little bit. You plug in, well, actually, the APX. You know the APX is a negative 1.6. You plug it in right there, negative 1.6 I, and then you just add everything up, and you get an I piece and you get a J piece. If you notice, what it's telling you is B is accelerating to the right, and it's accelerating down. Which kind of makes sense because B is on a curve and it's kind of winding itself around like this, so it's coming down and inward, and so it should be accelerating in and going down. I didn't bother to do the calculation with a calculator, but that's pretty simple. Just 1.6 squared. That's a magnitude, which is what they're asking for. So anyway, you get the direction. You can get the acceleration. The magnitude of the acceleration, that's what I calculated with the square root, and then the direction of the acceleration. I guess if they want it as a vector, then what you would do is you'd say it's going in by, what did we say, 1.6. Okay, so it's going this way at 1.6, and it's going down at 1.5. So it's a vector like this. So we can get this angle right here, tangent of theta, is equal to the opposite side, 1.5, divided by the adjacent side, 1.6, so you can get the angle theta. And they want it measured from the positive x-axis. So they want this angle here, like that. And so you'll just take, you get this one, whatever that number is, you take 360 minus the angle theta, bang, you get the value of the angle in degrees on the positive x-axis. Okay, that'll do that.